reason. Yes, so I just want, yes. And how carbon dioxide is a big reason for it. I would like to introduce Dr. Benjamin to the talk, and he's going to talk more about how carbon dioxide is removed from the atmosphere to build a better future. So before we start, I would like to mention that this program is being organized by AstraSTEM Labs in partnership with Grand River Malayali Association, NPHIL, Young Thinkers. I would like to thank our sponsor for this event, Vipin Sivadasan. And you can start.
Great. Well, thank you very much for inviting me, and I'm happy to be talking to you about this. Let me share my slides here before I forget. All right, can everyone see that? Hopefully. Good. Okay, so I'm Ben Tutolo, and I'm going to talk about carbon dioxide removal today, but first I want to talk about science and how I essentially became a scientist and why that's motivated me to get involved in climate change research. So how did I become a scientist? Ever since I was a very young person, maybe about 5 years old or even younger than that, I've been very interested in the outdoors and in particularly in fishing with my family. So this is me here in the green shirt showing the muscles. This is my older brother, Nick, and my younger brother, Chris. And since we were very young, we've been trout fishing, and I grew up in Western Pennsylvania in the United States, and I was a trout fisherman from a very young age, and that has always stroked my passion or spiked my passion into the outdoors and trying to understand the environment around us. At the same time, I have been in a sort of science-interested community since I was a very young person. This is me in the chair working the computer there. I've been, my dad is a systems analyst, so we were using computers at a very young age as well. So when it came time for me to go to university and start thinking about what I wanted to do as a career, I wanted to somehow combine my passion for the outdoors and my interest in science as a university student. And so I did my undergraduate degree at Penn State University, and I did that in environmental systems engineering. So I was interested in the environment, and I was passionate about the environment. And I also wanted to make sure that I was going to do something scientific. And I was also skilled at math. And so I was encouraged to become an engineer, not just an environmental scientist. So I became an environmental engineer as an undergraduate at Penn State. From there, I was really what spiked my interest as an undergraduate was geology and the geosciences. So thinking not just about the environment and what's active today, but also the way that processes and environmental processes have been recorded on our planet and on Mars throughout the history of both planets. So for the Earth is about 4.5 billion years old. We have a rock record from about 4 billion years of that time. And so we were able to look at rocks and understand climate change over those geological timescales. And so I did my PhD in this science, geology, the study of the Earth. I went onwards from there to Oxford University in the United Kingdom in England, and I spent 2 years there as a postdoctoral fellow. And I, got to do all the fun, enjoyable things that you think of when you think of Oxford, like the Harry Potter, like dinners and so on. But also I learned a lot about Earth's history and understanding how climate is recorded in the geological record as a postdoctoral fellow. And finally, I ended up here in Western Canada in Alberta. This is in Jasper National Park in Alberta. And I'm still fishing these days, and I have been this whole time. So throughout all of my pathway through science, I have kept my eyes and focused on the things that really excite me, like the outdoors. And at the same time, I've become a professor of science. So I do science daily. And the motivation through all of this has been what Richard Feynman called the pleasure of finding things out. So if you're curious about the world around you, you can become a scientist or use the tools of science to find out what is going on in the world around you. And that has always struck me as something that I've loved about scientific inquiry, but it wasn't until I read this book by Dr. Feynman, who was a Nobel Prize winner for his fundamental physics work, that I actually really was able to put words to that. So it's the pleasure of finding things out that has kept me going and active in this field for so long. So carbon dioxide removal as a climate solution, I want to talk about today just a couple of technologies that people are thinking about whenever we're thinking about removing carbon dioxide directly from the atmosphere instead of just stopping the emissions of CO2 to the atmosphere. But I'll go through the reasons why we might need to do that as well. So I'll take it step by step here. So this is a nice schematic of Earth's natural carbon cycle. So essentially, CO2 naturally enters the atmosphere through volcanoes. So those are the red arrows here. Places like the mid-ocean ridges, where we have volcanoes erupting on the ocean floor. Places like Hawaii, where there are volcanoes, Hawaii and Iceland, where there's volcanoes poking out of the water surface. Arc volcanoes, we're thinking like in parts of continents where you have a subduction zone. Perhaps you think of Mount Fuji, for example, in Japan. So there's, again, carbon dioxide coming out of those and entering the atmosphere. And continental rifting environments as well. This is like the East African rift today, where you are, again, exposing carbon dioxide from the mantle to the atmosphere. So over geological timescales, that's the main source of carbon dioxide to our atmosphere. Nothing having to do with humans and combusting fossil fuels and burning oil and gas, none of that. But also over geological timescales, the Earth has a way of taking that carbon dioxide back out of the atmosphere and making it back into rocks. I'm sure many of you have seen corals, for example, or other limestone rocks. Those rocks contain carbon that used to be in the atmosphere. So essentially what has happened is rocks on our continents, in our mountains, were dissolved by rainwater, washed into rivers, washed into the ocean, combined with carbon dioxide, and became rock over geological timescales. And so what's happening naturally is our planet has remained habitable for at least 4 billion years. For at least the past 4 billion years, it has had liquid water that we can go and swim in. It's not too hot, it's not boiling, it's not completely dry, and it's not frozen for 4 billion years. And that means that this feedback between carbon dioxide injection into the atmosphere and its removal by geological processes is approximately in balance. So this is lots of numbers, and I don't really want to focus on this too much, but just really want to point out this number here. So the amount of carbon that is in the atmosphere, these numbers are in gigatons of carbon, is actually really small. The amount of CO2 or carbon in the atmosphere compared to, for example, the amount of carbon in the surface ocean or the deep ocean, or in plants and animals and people, all the terrestrial biosphere, is much smaller. So it's about half that, or even a quarter of that, which is locked up in plants and animals and other stuff. It's much smaller than that, which is in sediments and the deep ocean by at least a factor of 10 or more. And so what that's telling us is that it's a very delicate balance that allows the atmosphere to have just enough CO2 to keep it warm, but not too much to make it too hot, essentially. And what has happened as we humans have been combusting fossil fuels, so we've been getting better and better at digging up oil and gas reserves, burning them in our cars and our planes and our power plants. What has happened is we've really outstripped the total amount of CO2 that the Earth naturally puts into the atmosphere. So the burning of fossil fuels and the manufacture of cement released 31,000 teragrams of CO2 into the atmosphere. This is a number from 2009. It's dated. It's only gone up since then, so this is a conservative number. And I'm sure none of us really understand what a teragram is, but just think about it as a really, really, really big number. In volcanic regions, annually, so all of the CO2 coming out of all of the volcanoes on Earth in a typical year release about 300 teragrams of CO2 per year to the atmosphere and the ocean. What that means is us humans burning fossil fuels and making cement are beating the Earth in its natural CO2 emissions processes by about 100 times. So we're emitting 100 more times CO2 than the Earth naturally puts into the atmosphere. And that's a lot. That's why the climate is warming so quickly, because we are going at a pace that is far, far faster than what the Earth is naturally doing. And so our human impact on the climate is gigantic. So this is a plot of temperature changes from the year 1901 to 2012. This has been updated in the last couple of years, but this is a useful example, and the new plot doesn't look much different. But what you see is that the whole planet essentially has been warming. All these numbers are essential, or all the colors on this map are reds and oranges and yellows, which means they're all above zero amounts of change, which means that they've been warmed over the last 100 and 110 years or so. And what that means is that us putting CO2 in the atmosphere at a rate about 100 times of what the Earth naturally does is having a huge and rapid impact on the global temperature. And this is just something else I like to think about because I work on lakes, and I think about the way that lakes and their geochemistry matters for plants and animals and biological evolution. And this is just a projection of changes in the number of lakes, so lake abundance, from the year 2009 to 2050. So this is a modeled number, but it is interesting nonetheless. What this shows you is that many places, particularly in North America, are going to get much drier. There's going to be fewer lakes. We're going to have lots of interesting problems with fresh water. But at the same time, and this is why sometimes folks call global climate change global weirding, some places are going to get wetter, right? So it's not all a one-way street. It's not all getting drier. It's not all necessarily getting hotter. Some places are going to get wetter with climate change, which is an interesting paradox. This brings me to one of the biggest challenges of the 21st century, the information-preparedness paradox. And in simple words, what that means is we know a lot, right? So at this point in human history, we know more than we ever have at any other point in human history. And we know now that humans' impact on the climate is gigantic, right? Our ability to dig up fossil fuels and burn them far outstrips the planet's ability to take that carbon dioxide out of the atmosphere. But, and this is the paradox part, are we prepared to do anything about it? So I see that our premier has made a very dramatic commitment to taking steps towards net zero. So he wants to cut emissions 40% by 2030. So those are, we are now making commitments to do it, but are we actually going to do it? And that's the question that we have today. And so this climate problem can be split up into what are called stabilization wedges, or little slices of carbon dioxide emissions that we can then make up in order to get total amounts of emissions to be net zero, and then eventually decreasing, which is the carbon dioxide removal stuff that I'm talking about today. And so this original study was in 2004, and they at that time had 1, 2, 3, 4, 5, 6, 7 wedges in order to get the carbon dioxide emissions at that time down to net zero and eventually decreasing. And what we now know is that because we haven't really corrected our ways, that this is more like 10 or 14 wedges in any case that we are going to need to do. And so essentially each one of these is 1 billion tons of CO2 per year by 2050. And you might have heard about this technology called carbon capture and storage. I know here in Alberta, it is talked about a lot. So this is taking CO2 from places that make energy, like a power plant, capturing that CO2 and then injecting it into the subsurface. And so this is very popular technology in Alberta. We have one of the largest in the world injection operations right now. And Alberta is continuing on this route. So Alberta asked recently, this is about a year ago now, the government to commit $30 billion to advance carbon capture technologies. I can just substitute in a more modern news story that says exactly the same thing. Essentially, we are still committed to CCS. And so if we want to put carbon capture and storage in this framework of wedges, what would that look like? Sorry, is there somebody that could turn the microphone off? I can't see who that is. Alberta's coal-fired gas by the end of the century, or by the end of this decade, sorry. But if we just put that in perspective, gigawatts are a lot of electricity, and that's how much Alberta makes. So essentially, in order to get to one of these wedges, and we need about 10 or 14 of them in order to get to net zero, we need approximately to remove all of the CO2 emissions from 150 Albertas. Obviously, everyone knows that that's not realistic, right? There's so many, or there's only so many provinces in Canada, right? So there's not 150 provinces in Canada, not even close. And so there's only like 180 countries in the world. So this is really quite a dramatic number. But yeah, essentially, in order to get to 8, we only need to do 7 more Albertas, right? So this is essentially putting the climate challenge into context. We need to do a lot of carbon dioxide capture and storage in order to get anywhere. And so what I would say, if you ever hear about CCS and what you should think about when you hear about CCS, carbon capture and storage from coal and natural gas fired power plants, essentially it's feasible, it's fairly straightforward and secure. The only reason that people aren't doing it more often is because it costs a lot, right? If somebody says, hey, you could do the same thing, you can make the same amount of electricity, except you got to pay a lot more in order to capture and remove your carbon. If they're not required to do that, they're not going to do it, right? And so that's exactly what the issue is today. So CCS is not happening at wide scales because it's not required. And so I believe that we should definitely do CCS. And I think in places like Alberta with large greenhouse gas footprints, it's going to definitely happen. It's going to definitely be an integral part of our pathway to net zero. But even if we do this at all of our CO2 emitters all over the planet today, we're still probably going to rise above 1.5 degrees Celsius of warming. And that's the threshold above which it's too hot, essentially, for many of the hydrological and ecological systems on our planet to function realistically and well. And so this is a complicated plot, but essentially what you need to be looking at is, in order to get to a habitable environment here, so that we're not in 100 years from now going to be on a place that's essentially burning up and impossible to live on, we're probably going to need to do negative emissions or carbon dioxide removal. And so that's what this blue color here is in the bottom. Essentially, after the year 2030 or so, we need to start ramping up carbon dioxide removal technologies so that by the end of the century, we will have a very significant amount of carbon dioxide removal. And so these technologies essentially are at extraordinarily small scales today in 2022, but by the end of our century, so by the time you folks are all grown up, it should be that these are taking a huge bite out of the carbon dioxide budget. And so it's projected that we're going to need about 10 billion tons, 10 gigatons of CO2 removed from the atmosphere each year by the year 2050 in order to be in a place where we are actually meeting net zero targets and staying below 2 degrees Celsius warming. So this guy, Bill Gates, he was probably more famous whenever I was younger than he is today, but he is a very famous person. He's very, 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 very rich. And so what he has committed to do is funding energy breakthroughs that are going to allow us to meet this incredible target. So essentially, we're going to need to remove approximately, in order to get to net zero, we need a way of getting 50 gigatons or billions of tons of CO2 of emissions per year to not go into the atmosphere. So he put in $1 billion, or he and his colleagues put in $1 billion into what they call the Clean Energy Fund. And these folks, what they say is that we're only going to support technologies that are capable of potentially removing 1% of annual emissions, or 500 million tons per year. So that's a lot. So all of our emissions total is about 51 billion tons per year, gigatons per year. If you want funding from Bill Gates' organization, you need to be able to do 1% of that, or 500 million tons per year. And here's a nice quote from Mr. Gates. My basic optimism about climate change comes from my belief in innovation. The conditions have never been more clear for backing energy breakthroughs. It's our power to invent that makes me hopeful. So he is relying, and I think I agree with this completely, on our ability to think up ways of solving the climate crisis in order to get to net zero and keep our planet habitable and equitable. So I like to say there are plenty of seats for optimists at the carbon dioxide removal table. So as I said, essentially these technologies are not really being used at all right now. They're just in the very beginning stages of development. But by the end of this century, we're going to need to have significant amounts of carbon dioxide removal. And so you have to be optimistic about how we can do this. So the most successful version of this so far has been CarbFix, which is a project in Iceland. Essentially what they do is take volcanic rocks basalt, which Iceland is made entirely of, combine it with CO2 that's been dissolved in water, pre-dissolved in water, and what they do is turn that into rock. And that means that that CO2 is no longer in the atmosphere. Exactly the same thing that the Earth does naturally. So it takes basalt or other rocky materials, combine them with CO2 and makes carbonates. And so the Earth does this naturally, CarbFix proposes doing it faster. This is a schematic of how it works. They have some power plant, for example, a coal or natural gas fired power plant. They strip off the CO2 and suck up some water from the ground, mix them together, and then inject that CO2 charged water as something like a Perrier or a Soda Stream water, some nice sparkling water that they then inject into the ground. That water interacts with the rock and becomes a solid carbonate mineral like limestone. The project that I'm working on, that I'm most involved with, is called solid carbon. And so this is a Canadian technology, which is super fun and exciting for us living here in Canada. What we do is we, again, propose capturing CO2, not necessarily from a coal or natural gas fired power plant, but instead directly from the atmosphere. So using what are called direct air capture machines, so machines that can capture CO2 directly from the air, pressurize it, and then pump it deep below the seafloor, again, in order to turn it into rock. Yeah, so this is us here. So we have been working on this project with the solid carbon team since about 2019 now, so a number of years. And our main focus right now is to inject CO2 into basalts. And so these are basalts all over the world. There's us here in Canada, right? And right off of the western coast of Canada, there's an enormous amount of basalt, this orange color here, in what is known as the Cascadia Basin. So if any of you have ever been to or heard of Victoria Island, or Vancouver Island, where Victoria is, essentially right off the coast of there, Canada has something called Ocean Networks Canada Observatory, and out into the sea, we have fiber optic cables going directly to the sea floor. So we have cameras and instruments and all kinds of interesting science going on right out there off the western coast of Canada. And we're proposing to inject CO2 there so that we can use then those fiber optic cables to transport back the data about the carbon dioxide injection and removal process. But what this plot should show you is that all over the globe, there are lots of basalts that could potentially be utilized to remove carbon dioxide from the atmosphere. So what is the global carbon dioxide removal capacity of basalt? Theoretical storage is enormous. It's approximately 100,000 billion tons of CO2. And that is an enormous number. It's hard to even think about that. 100,000 billion tons of CO2 is more CO2 than would even be produced if we burned all of the oil, gas, and coal on the planet today. That would produce about 18,000 billion tons of CO2. So this is approximately 10 times more capacity than we would need in order to mineralize all of the CO2 that would be produced for burning all of the fossil fuels on the planet. But right now, unfortunately, the global carbon dioxide capture and storage capacity is about 40 million tons per year. And to scale that up to 100,000, or to scale that up to 1 billion tons per year, you would need approximately 100 times scale up. CarbFix, that project in Iceland that's been the most successful to date, injects about 12,000 tons. So we're not talking billions of tons, we're just talking tons of CO2 per year. So you need to scale that up by about 100,000 times. That's a 1 with 5 zeros behind it. It's an enormous number, but again, there's plenty of room for optimists at the CDR, carbon dioxide removal table. Another proposed carbon dioxide removal technology is taking that same material, taking basalts, grinding them up into a really fine powder, which here turns out to be green, and then putting that onto agricultural fields. So places where they're growing, in this case, wheat or corn or barley or whatever, you put the crushed mineral out onto the field. And what that does is then takes up extra CO2 from the atmosphere whenever you're growing those plants. It also helps out the plants. So it also is a fertilizer as well. So the net carbon sequestration capacity is approximately 1 billion tons of CO2 per year, which is shown here. And so that would involve lots and lots of these enhanced weathering operations across Canada, as you can see in these red colors here, but in many other parts of the world as well. So the projected capacity, if we do this so-called enhanced rock weathering, so crushing up rocks and sprinkling them on croplands, is on the order of 1 billion tons per year. So 500 million to 2 billion tons per year. China, the United States, and India have the highest potential for CO2 removal via this technology. Canada also has significant chance, but because we have long winters here, ours is lower than theirs. But enhanced, and I guess the other advantage is that enhanced rock weathering, the sprinkling these rocks onto croplands, increases soil pH and gets more crops. You get more corn whenever you do this technology. So there's plenty of room for optimism. So farmers might want to do this regardless of whether they're removing CO2 from the atmosphere or not, because they are actually boosting the yields of their plants. Another new, and I think a little bit more hard to conceptualize weathering technology is what they call magnesium oxide looping, or MgO looping. And in this case, what they're doing is taking rocks, so limestone again in this case, cooking it at a really hot temperature, like 700 degrees Celsius or so, getting all of the CO2 off, capturing all of that CO2, and then reacting what's left, so essentially it's a magnesium oxide at that point, with the atmosphere, waiting for a year, and then essentially injecting that and doing the same thing again, cooking it, capturing the CO2, and injecting it. This technology would require approximately 6,100 square kilometers to get to 1 billion tons per year. This so-called Nevada test site is a place where they tested a bunch of weapons back in the Cold War era in the United States. Requires or has a area of about 15,000 square kilometers. So this would enable you to get to 2.5 billion tons of CO2 per year. So very significant amounts, and it's quite feasible to do that there. Alberta, so where I live, has a surface area of about 661,000 square kilometers. Again, that number is so much larger than the amount you would need to get to 1 billion tons of CO2 removal per year that you start to think that this technology might really be worth trying out. So again, there's plenty of room for optimists. So take-home messages about carbon dioxide removal. There are at least 10, perhaps more, flavors or types of carbon dioxide removal that are out there in the world today that are being worked on actively, that are being funded by folks like Bill Gates. But to be effective, these technologies have to be implemented at an absolutely unbelievably massive scale. So 1 billion tons of CO2 per year, or 500 million tons of CO2 per year per technology. And we need at least 10 of them to work. So humans are already affecting the Earth system on an absolutely massive scale. So even though the carbon dioxide removal challenge sounds daunting, it's actually perhaps less daunting to think about the carbon dioxide removal that is required and why it's required. Again, so coming back to this, we're beating the Earth by 100 times. Right? We are emitting so much more CO2 than the Earth does naturally that even though these technologies sound a little bit crazy and a little bit like we might be changing the fate of the planet, we already are doing that. So the last question that often people ask whenever I give a presentation like this is, how much is this going to cost? So this is a projection of carbon dioxide or carbon prices per ton, dollars per ton of CO2 over the next 50 years or so. And what you see is that essentially throughout this century, the price is projected to be up towards $200 per ton of CO2. Even just this week, Prime Minister Trudeau said that we're looking here in Canada at a carbon price of about $170 per ton by the end of this decade. So it is happening, and things like that are going to cost. So essentially, many of us that work on carbon dioxide removal technologies believe that if we can match this number, if we can make the carbon dioxide removal cost the same amount as it costs to emit CO2, then we are successful. And again, many countries around the world, including Canada, already have these carbon pricing initiatives. So there is already incentive to remove carbon dioxide from the atmosphere instead of emitting it. But in the end, if you want to put carbon dioxide removal and its cost in context, we can think about cholera. So the case for how people should think about this was made by my colleague, Peter Kellerman, who is a professor at Columbia University in New York City. He said that, or what he summarized about cholera is that in about 1820, London, right, London, England, became the world's largest and arguably most important city in the world. It wasn't just the capital of Great Britain, it was the seat from which the empire's rulers controlled nearly half the world's population. But London, in some ways, was still backwater, right? It still lacked a central sewer system. So there was no way for the poop from all of the people in the city of London to go anywhere but into the streets. So people, what they were doing was taking their poop and putting it in the street. If you were rich and you had lots of money, you had a pipe that took your poop somewhere else, but still it was just sitting in a cesspool that was exposed to people that would be walking by. John Snow, who's now known as the father of epidemiology and who has been thought about a lot during the recent pandemic, undertook research that showed that the links between this poop that was in the street or sitting in pools around London caused at least 3 cholera outbreaks, which killed more than 30,000 people in the first half of the 1800s. To add to that, most of the human waste eventually found its way into the Thames River, so the big river that flows through London. And he said, I can certify that the offensive smells, even in, or this is Charles Dickens that said this, I can certify that the offensive smells, even in that short whiff, have been a most head and stomach distending nature. As he wrote that in a letter to a friend in 1857. So London had a very significant problem with cholera. And in 1858, there was a summer when it didn't rain. The Thames dried up and the stench got stronger. So all that poop in the street started smelling worse and worse. So this is like a big poop monster here in the street. And it was called the Great Stink. So London was a very stinky place. The Queen and the royal court left London. Members of Parliament debated moving out to Oxford from London, which is north of London. But fortunately, instead of leaving, what they did is they passed laws to do something about this problem, about how terrible and stinky the city of London was. And what they did is they dug up all of the largest roads in the world's largest city, so that was London at the time, and they installed sewers. It took about 10 years to do, and it cost about 2% of the gross domestic product. And even today, it costs about 1% of the gross domestic product, so this is just a measure of how much money a country has, to maintain the sewers that are in London. So no one questioned whether that was worth it, though, right? People were dying. It was smelly, and people were dying because of the poop in the streets. And so they committed this amount of money, 2% of the gross domestic product, in order to install sewers and stop dying and stop smelling. So until people think of throwing CO2 in the air, that it is something like throwing poop in the street, we're not going to spend what it costs. At 2% of global gross domestic product, we can make the CO2 problem go away. So even if these carbon dioxide removal technologies are expensive, if we think about the consequences, or the alternative is essentially having a place that is no longer easy to live on for our grandchildren and great-grandchildren, then we spend that money, we spend that 2% of gross domestic product, and we can make this problem go away. So just to conclude, if the future of humanity and all of Earth's organisms depends on carbon dioxide removal implementation, then costs really shouldn't matter, right? So we really shouldn't care about how much something costs if the alternative is death. But on the other hand, the other flip of the coin, is that money drives innovation. So the number of carbon dioxide removal startups that I have been contacted by and have been talking with is positively astounding. So many people are putting on their entrepreneurial hat and trying to start businesses that can remove carbon dioxide from the atmosphere. So the point is, we can do this, but we have to get started now. And so I know that carbon dioxide removal and climate change can be very sad. So I leave you with sunshine, lollipops, and rainbows. And I'm happy to answer any questions that you folks might have. Aaron, do you have a question?
Why did those people throw their I don't like saying the word, but why did they throw them in the streets?
Because they didn't have toilets.
Oh, and how did those people die from that?
there was diseases in their poop
Oh,
that got other people sick, and they got really, really sick and died of a disease called cholera.
oh well, thank you for answering.
Yeah. Adhirth, did you have a question?
It's address and first of all, if the CCG is putting carbon dioxide in the bedrock, won't it pollute the groundwater?
That's an excellent question. And the main goal is to not ever pollute groundwater, right? Groundwater is a precious resource, and if we pollute that, then we run out of one of our most important ways of getting water for people to drink and to irrigate crops, etc. So what we do is inject it into what are called deep saline aquifers, so far deeper than where anyone is pumping drinking water from. And these aquifers are so deep and they're so old and the water is so weird, it's so salty that you would never be able to drink it anyways. And so we put it into those where it's not drinking water at all, it's actually just completely unused water in the deep earth that we're talking about putting CO2 into.
Thank you.
Lakshmi asks if there are any negative impacts to getting rid of carbon dioxide through the basalt. And so it's sort of an interesting question to think about. So as I said earlier, that the Earth is essentially doing this naturally, right? So it is already taking basalts, interacting it with CO2 and making it into the limestone rock that we see today, all covering the oceans. And covering into, for example, the Rocky Mountains here in Western Canada. So the Earth is naturally doing this, but of course we're talking about it doing it at a much larger scale and much faster than the Earth naturally does it. So the negative impacts that we can think of are essentially what is already living there in these basalts. And so in most cases, there's no animals that would live in a basalt like this. They're in the deep subsurface, the deep ocean, where you probably would only find bacteria that living there. And so one of the potential consequences is you either feed these bacteria lots of carbon dioxide and they get really happy, or perhaps that carbon dioxide poisons them and you kill them. In any case, they're bacteria, so it's not as if we're killing whales or anything like that. But on the other hand, the other potential consequence that people are worried about or think a lot about is there going to be an impact through leakage of the CO2. So what happens if the CO2 leaks back into the oceans or just leaks back into the groundwater that overlies the basaltic aquifer that could potentially be drinking water? And so those are potential risks. So the advantage to basalt is that it is highly reactive. So it should turn that CO2 into rock fairly quickly. And so that risk of leakage in groundwater contamination and or leakage to the surface is much lower in the case of basalt than this in many other systems. So those are the potential negative impacts. All right, Malavika asks, do you think it's better to just stop carbon emissions instead of capturing the carbon emissions from the atmosphere? I think we have to do both, unfortunately, right? We sort of have waited way too long since we knew about climate change and knew that our enormous amounts of CO2 emissions were causing warming in order to do something about it. So we're so late in the game now that I think our projections or our models of the future climate suggest that no matter what, we're going to have to remove some CO2 from the atmosphere. So while I think that it is extraordinarily important to decarbonize all of the things that we do, drive cars, fly planes, make energy, I think that that's going to happen. So we need to stop emitting carbon. But at the same time, even if we did that, even if we captured all of the carbon that's being emitted today, it seems that we would still emit, or we would still rise above 2 degrees Celsius of warming. And that means that we still need to do something else in order to stay below 2 degrees Celsius warming. And what we're talking about then is removing carbon dioxide directly from the atmosphere. So although it is much more desirable to have, say, 20 years ago started down this path of emitting less CO2, because we haven't, because our emissions have only been growing, we're sort of faced with the problem now that no matter what, we're going to have to remove CO2 from the atmosphere. Miriam asks, what about emissions from vehicles? And I think that's a really good question, right? So the problem is, if we're driving our gas or diesel powered cars, where does that CO2 go whenever you drive? And it goes directly into the atmosphere, right? There's no tank on the back of your car that's capturing that CO2 for you. And so that's why folks like Elon Musk and so on are talking about having electrical cars, right? So then we charge them and then we can capture the CO2 at the power plant instead of at the back of the car. But carbon dioxide removal has the ability to sort of allow those more intensive vehicles like dump trucks and so on that are going to be sort of very difficult to design big enough batteries for. CO2 removal allows us to then still allow those trucks to be on the road, perhaps more efficient, still emitting some CO2, but then still be at net neutral or net negative emissions, or net zero emissions, sorry, by removing then the same amount of CO2 from the atmosphere. And so you balance it, whatever's being emitted from the cars and trucks, by removing the same amount from the atmosphere. Okay. If Shauna asks, how do I ask questions? You could certainly type your question in the chat, or if you would like to speak now, I'm happy to answer your question.
Oh, yeah. How does the waste get infected? Like you said it before, get diseases in the waste. How does that get affected?
Yeah, I mean, it's natural, right? So our bodies are full of microbes. Most of them are very good microbes and we're not sick, but some of them are bad microbes, right? And so that's the same thing that's been happening with COVID, for example. We've been using wastewater around the world to monitor for how much COVID is in our wastewater. It's the same sort of process where somebody gets sick with cholera, for example, it passes through their body, it goes into their waste, and then that is infectious for the next person to potentially get. So that's how that works. Adrith, right? Am I pronouncing it correctly?
Iris.
I'm close. I'm sorry. I will get it. So what about methane emissions from cows? I think methane is our big problem right now, right? I think a lot of us are really thinking a lot about CO2 and how we're going to get the CO2 problem dealt with, right? Because we know how we make CO2, right? CO2 is made from burning fossil fuels, burning oil and gas. But methane, and especially methane from animals, is a much more amorphous problem, right? And unfortunately, methane is a much stronger greenhouse gas than CO2. So although it breaks down in our atmosphere much quicker than CO2, methane is a much stronger greenhouse gas, so it has the potential to warm our planet even more than CO2. So methane emissions from cows and other animals, the way that we're thinking of dealing with those is kind of all kinds of crazy stuff. So I've heard of very funny sorts of proposals, and these are serious, so scientists are seriously working on this. Something that, for example, would go into a cow or go onto a cow that would then burn the methane that comes out of that cow, so essentially from cow farts or cow burps, burn it and make it into CO2 instead of methane, and then we have CO2 in the atmosphere instead of this incredibly potent greenhouse gas, methane. So it's a big problem. It's hard to deal with. Go ahead.
And how do you prevent it? Like, if without cows, we won't have milk. Right? Or without goats, we won't have goat milk.
I agree. Yeah. And I think that I'm not sure that you can prevent it. I think if you think about it that way, and all we need cows for is milk and not necessarily meat, then you can reduce the amount of methane emissions quite substantially. But that's not for me to say, right? So I think what we have to do, and again, this is this concept of net zero, is that some stuff is going to be very, very difficult to ever stop emitting from, right? So perhaps cows and perhaps certain types of airplanes are always going to be emitting a little bit of CO2. So we need to make sure that on the other side, we're removing at least that much CO2 so that we can be at net zero emissions.
Yeah. So, and one more question. Can we use the same technology to capture CO2 from methane?
Yeah, so and this is the same sort of thing that I was getting at before, is like so cows move around, right? So they're not like a point in space. And so we don't really have a way of just like we do with power plants, just putting something on the power plant that captures the CO2 for us, for example. But methane, right, that comes out of a cow, and that's why folks are talking about putting something onto a cow that burns the methane, makes it into CO2, and then we can deal with the CO2 perhaps in a different way. But it's a really challenging problem, methane. Okay, Darsh, I believe, asks if CO2 has any benefits, and the answer is yes, right? The biggest one, of course, is the one that we all know, right? Is that without a greenhouse, our planet would be very, very cold. So Mars, for example, has lost most of its CO2 in its atmosphere. Its atmosphere is much less dense than us. It has much less CO2 in it. And Mars is now a very, 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 very cold place most of the time. Sometimes it gets hot whenever it's on the right side of the sun, but for most of the time, it's very cold. And what that means is that CO2, you would need to have more CO2 on Mars in order for it to be habitable. And it's thought maybe in the ancient past, 3 billion years ago on Mars, there was enough CO2 in the atmosphere for it to be warm enough to potentially support liquid water and potentially life. So the main benefit of CO2 is that it is why we are all here, right? Without the greenhouse, the CO2 greenhouse, we would never have enough heat on our planet to stay warm enough to not, to stay warm enough to live, right? So that's its main benefit, right? There's also lots of other benefits, right? Plants need CO2 to breathe, right? So plants turn CO2 into oxygen, right? So without any CO2 in the atmosphere, you couldn't have plants. Without CO2, you probably, again, you couldn't have us because it wouldn't be habitable. Also, lots of other life is dependent upon the existence of CO2. And there's also other things, like for example, CO2 can be used as a solvent. So people are using it, for example, for dry cleaning or for taking flavors out of tea leaves and so on. So CO2 actually does have numerous benefits that you wouldn't necessarily think of at first step. So Lakshmi, is there something like basalt that can absorb methane? Unfortunately, not really. So the only thing that we can really do with methane is turn it into CO2, and then CO2 is much easier to deal with than methane. Methane is essentially so it is a different oxidation state than carbon. What that means is that methane is food for some creatures that wouldn't otherwise be able to eat CO2. But if we take those creatures, get the methane into CO2, and then, or if we just burn it, right? So if we just burn the methane, then we can make CO2 and then deal with the CO2 in these ways that I'm talking about. But in general, methane is not particularly reactive, so there's not much we can do with it. We can't turn it into rocks, for example, without first turning it into CO2. Now, Vika asks, so doesn't the technology need to be very careful on how much CO2 it takes from the atmosphere? And that's an excellent question. I think right now we won't have that problem because most of these are so inefficient to get to the right level. It would be an enormous stride in the technology to get there, but it is right? So what if we take out all of the CO2 from the atmosphere? Exactly what I was just talking about would happen. What would happen is it would get really cold, right? And we would have a snowball Earth, which has happened at certain times in Earth's past. And so that ability to turn off the removal, right, to stop removing CO2 from the atmosphere is, to many of us, a very important piece of the technology, right? So if you do something like, for example, making special particles to put into clouds, right? Once those particles are in the cloud and reflecting sunlight back into space, then we have no way of turning that off, right? They're just up there. We can't get them back. But with these carbon dioxide removal technologies, they're almost always a machine, right? There's something that has a power button, essentially, or a plug. And we just unplug it and it'll stop. And so those sorts of fail safes, the ability to stop it once it's started, are extremely important for all of these technologies. Any other questions?
Not that there are no questions.
All right, thank you all for attending, and I hope everyone has a lovely weekend.
All right, so if we don't have any more questions, I just want to once again thank everyone for coming. I want to thank our guest speakers for being here. And I just wanted to again mention our partnerships with Grant River Manili Association and NPHIL Young Thinkers. We would also like to thank our sponsorship once again for this event, Vipin Sivadasan. And I hope everyone has a great day.
Indeed. Have a great weekend, everyone.
Bye, guys.
Bye.